Now we're going to spend some time studying a topic that many of us encountered in elementary school or middle school, and that's integer division. How do I divide one integer by another integer? This topic, when we learned it in elementary school or middle school, we might have focused on kind of how to do it. We sort of got a mechanical algorithm. Here, what we're going to do is we're not going to focus on a mechanical algorithm at all. Instead, we're going to focus on the definition of what it means to divide one integer by another. We're going to get some practice with that definition, and we're going to use that definition in order to help us think about modular arithmetic, an important concept in computer science and applied mathematics. Along the way, we are going to build our comfort writing proofs and thinking about proofs as a process of writing. So, let's jump right into integer division. So definition, let a and b be integers. The integer division representation of a by b is an integer k and a natural number j. So I'm supplying two additional numbers beyond a and b with two properties. So the first property that I require from my candidate choice of k and j is that a is equal to k multiplied by b plus j. Okay, so that's my first requirement. What this says is that in order to make up a, what I need to be able to do is I need to be able to take k copies of b and then add j, and the result has to make a at the end. And then second, I require additionally that j must be less than the absolute value of b. Note that j is always non-negative because it's a natural number, so j can't be a negative number. So, uh, additionally here, what we're going to do is we're going to say, define a special term here as well. If it's the case that j equals 0, we say that b divides a, which is written using a vertical line, b vertical line, a, b divides a. So there's some familiar terminology floating around here. So we've all heard of integer division. Maybe the idea that one integer divides another is relatively familiar as well. There's a few vocabulary words going on that you don't need to remember, but can be useful to have in your back pocket or in your notes. So a, the thing that is being divided, is the dividend. B, the thing that is doing the dividing, is the divisor. K, the result, the number of times that the divisor can be taken from the dividend, is the quotient. And J, what's left after you've taken a quotient number of copies of the divisor from the dividend, is the remainder. So a little example here. Let's consider A is equal to 11 and B is equal to 3. So we have many candidate ways that we could write this roughly in the form that corresponds to condition 1 here. So for example, I could say that 11 is equal to 1 times 3 plus 8. That's a true arithmetic equation. Here's another one. 11 is equal to 2 times 3 plus 5. Okay, so these have the right form. I have a candidate for k here. So in my first example, k would be equal to 1 and j would be equal to 8. But we wouldn't say that 11 divided by 3 is 1 with remainder 8. That's not really how we normally talk about that. Similarly, we wouldn't normally say that 11 divided by 3 is 2 with remainder 5. There's only one integer division representation of 11, actually, that also satisfies this second condition here. I've satisfied the second condition. And that is 11 equals 3 times 3 plus 2. So we can check. 2 is less than b, so b here is 3, so 2 is less than 3 in absolute value, so I'm good. And that means that this expression is the integer division representation of 11 by 3. I have a quotient of 3 and a remainder of 2. The integer division representation is in fact unique. There's only one for every pair of integers, and that's something that we will be able to prove later. Now we're ready to introduce modular arithmetic, which is a very helpful form of arithmetic in computer science. You've seen it if you've ever looked at an analog clock, where we start at 12 midnight and then we go around the clock. And then after we go around the clock, we haven't gone on to 13, but we go back to 1. So modular arithmetic is a generalization of this idea. Here's our formal definition. We start with an idea of what we're going to call modular congruence. So we say that integer a is congruent to integer b modulo p. So say this, if you want to pronounce it, a is congruent to b modulo p. So we say that a is congruent to b modulo p if both a and b have the same remainder when we divide them by p. This might feel a little abstract, but here's a simple example. So let's consider a equals 3, b equals 5, and p equals 2. Okay, in this case, what we need to do in order to check if a and b are congruent modulo p is to form the integer division representations and see if they have the same remainder. So here, if I check that the integer division of a, so 3 is equal to 2 times 1 plus 1. So 1 here is my remainder. Then, if I check 5, 5 is equal to 2 times 2, again plus 1. 1 is my remainder. These match, and so because of this, I can conclude that I've satisfied my definition. It's the case that 3 is congruent to 5 modulo 2, because when I divide 3 and 5 by 2 in integer division, I get the same remainder. And that satisfies my definition of modular congruence. There is another useful formulation for modular congruence that can help us out. And so what I want to do is I want to actually prove this formally now, show that these two formulations are equivalent. That means we can use both of them whenever we want to. So theorem. It's the case, or the following are equivalent. That's another way to say this. The following are equivalent. A is congruent to B mod P if and only if P divides A minus B. So remember, this means that P divides A minus B without remainder. The remainder is 0. So these are two equivalent definitions. I can check either one. I can either check the formal definition of modular congruence, they have the same remainder when divided by P, or I can simply check that P divides A minus B. So let's write a proof of this. This is a good case for showing direct proofs. We have to make sure that we prove both directions here, because if and only if means that the left-hand side implies the right-hand side, but it also means that the right-hand side implies the left-hand side. So what I'm going to do is I'm going to prove each one. First, we'll prove the right-hand direction. So, suppose that A is congruent to B mod P. What I want to show now is that this implies that P divides B minus A. So what do I know if A is congruent to B mod P? I know by definition that A and B have the same remainder. So let's operationalize that. I'm going to say, okay, A is equal to P times J plus K, and B is equal to P times L plus K for some integers. I don't know what they are, but I know they must exist. J, L, and K. And the important thing to note here is that it's the same K that's the remainder of A and the remainder of B. So let's now look at the difference. So A minus B is equal to Pj minus Pl, and the k's here are going to cancel out. I'm going to add a k and subtract a k, so I'm not even going to write it here. So I can also factor out the p here and write j minus l all multiplied by p. And this is clearly divisible by p because we can see the factor of p right here. So that means if I divide this by p, my quotient will be j minus l, no remainder. So I can conclude that a minus b is divisible by p. I've proven the first direction. I've shown that if a is congruent to b modulo p, then it must be the case that p divides a minus b. Now, let's go in the other direction. So next, we'll prove the other direction. Okay, so to do this, suppose that P divides A minus B. P divides A minus B. Then it must be the case that there exists an integer that I'll call h in Z with the property that P times h is equal to A minus B. So that's the definition of one number dividing another. So now let k be the remainder of the integer a by p. Then, by definition, it must be the case that a equals p times j plus k for some j. Okay, it follows that p times h, which we already know is equal to a minus b, is also equal to p times j plus k minus b. We've just substituted in our expression for a. And if we rearrange this, we'll find that b is equal to p times j minus h plus k. Now, this is our punchline in this direction because we found that, okay, k was the remainder of a when divided by p, but k is also the remainder of b when divided by p because we have checked, okay, we've written b in this integer division form. Okay, so we know that b has the same remainder by when divided by p as a, as was to be shown. So our proof is done because first we proved the rightward implication that if A is congruent to B mod P, then P must divide A minus B. And then we proved the leftward implication that if it's the case that P divides A minus B, then it must be the case that A is congruent to B mod P. So for now, we can actually treat either of these two properties as equivalent. If we want to talk about modular congruence, we can say either this definition have the same remainder, or we can say that P divides A minus B. Either of those will work.